Language models process information efficiently in isolation, but when you drop a multi-directional enterprise workload into a closed system, the machinery suddenly seizes up. We currently treat highly capable models as if they belong inside a text box. That confines the model behind a glass wall, entirely separated from the environment where your actual work lives. An isolated model cannot read the pull requests in your GitHub repository. It cannot audit your Stripe billing portal, and it cannot query your Postgres database. It can only advise. To bridge that gap, engineering teams have been forced to write custom API glue. Every single integration requires defining tools, authenticating protocols, mapping schemas, and handling errors entirely from scratch. That brittle architecture is breaking. We are moving away from custom glue toward an industry-wide standardization of the agent stack built on specific network protocols. Looking at this minimalist architecture schematic, you can see the central LLM node is surrounded by three requirements. First, what can the agent use? That is reach. Second, who else can it work with? That is delegation. Third, how does a human intervene? That is control. As we fill in the pillars, they map to three emerging protocols: MCP, A2A, and AGUI. Mastering these three network layers is the required step to transition a language model from a passive advisor into a trusted autonomous system. The first protocol, the Model Context Protocol, or MCP, acts as a standardization layer. It allows a host agent to automatically discover and invoke external systems. MCP solves the integration bottleneck. A single standardized pipeline replaces the tangled mess of API wrappers, providing a universal description of executable tasks. But granting access isn't a simple feature toggle. As the agent punches through to external databases, it crosses a critical security boundary. MCP is designed to get tasks done. By definition, that means it enables arbitrary code execution and arbitrary data access. This introduces a vector researchers call tool poisoning. The attack hides malicious instructions inside the tool description metadata. Because the protocol relies on this metadata for discoverability, the poisoned packet travels backward, directly influencing the agent. MCP was built for high-trust environments. If you are shipping an MCP server, you have to actively build the trust layer yourself, configuring strict scopes, approval flows, and audit trails. MCP succeeds at bringing the agent to the work. It does not possess the logic to decide if the agent should do the work. Without oversight, it creates a massive supervision debt. Once an agent has reach, it hits an expertise limit. No single model holds infinite context, nor can it manage permissions across every corporate domain. If you deploy a procurement agent to onboard a new software vendor, it cannot authorize the purchase alone. It needs a specialized security reviewer agent to vet the compliance documents. This is where agent-to-agent, or A2A delegation protocols come in. As the central model scales down and connects outward, the protocol turns distributed corporate work into an architecture agents can mathematically reason about. The foundational primitive of this layer is the agent card. The agent card operates as a strict operating contract. It explicitly lists what the remote agent is, what skills it exposes, and the exact protocols for reaching it across company and product boundaries. Coordination carries a high cost. A2A protocols inherently introduce new latency surfaces, permission conflicts, and observability black spots. You deploy A2A only when a workflow strictly requires delegated expertise or authority that sits outside the primary agent's permissions. The agent card solves the problem of cross-domain capabilities, but expanding the network vastly increases the unpredictability of the final output. We now have a compounding risk. The system has arbitrary tool access through MCP, and it is delegating tasks out of sight through A2A. Traditional web applications fail to manage this risk. They are built for synchronous call-and-response interactions, not the continuous streaming reality of long-running agent workflows. The open candidate for the human control layer is the agentic GUI, or AGUI protocol. Looking at the network level, AGUI dictates how a backend system shares state. It pauses the workflow, allowing steering mid-task by connecting to a human control node. Humans can observe new information, injecting a confirmation signal to approve or deny sensitive steps before execution resumes. This is distinct from Google's A2UI protocol. A2UI solves a narrower front-end rendering problem. It ensures agents return structured, declarative UI components instead of executing arbitrary HTML code. teams frequently wire up tools and models first, only to realize in production that they lack the architecture to render progress spinners, event logs, or approval buttons. Without an AUGWI layer enforcing control points, an autonomous system becomes a black box that shatters human trust the moment it touches external infrastructure. This trust dynamic is tested most severely at the most contested layer of agent workflows, authorizing the autonomous spending of money. Google's AP2 protocol attempts to establish commercial trust. It relies on a mandate, a cryptographically signed proof of what the human user explicitly authorized. Contrast that with Coinbase's X42 protocol. As this split screen shows, AP2 on the left requires a looping check back to the user. On the right, X42 executes rapid, continuous exchanges between two machines, designed specifically for machine-to-machine micropayments for resources like API calls. Choosing the wrong backend substrate directly impacts your front-end customer experience. If you select a human mandate protocol with a short-term token for a background task, the system will request reauthorization every 30 minutes. You will generate an incredibly frustrated user. Network protocols are naturally opinionated. They carry built-in assumptions about regional geographies, payment methods, and user behavior that dictate how the final product feels. Between MCP's reach and AGU's control, these protocol layers act as the primary architecture defining the final product experience. Right now, we are watching chaotic manual integrations rapidly slotting into a perfect grid, creating a smooth, unified architecture. To succeed in the agentic economy, architects need to stop obsessing over LLM model selection and start defining the strict boundaries of their operating surface.